Hi, my name is Reimers, and I thank you for the opportunity to present my work here that I've done together with Bodesheim, Jakob, Runge, and Joachim Denzler at the Friedrich Schiller University in Jena and the German Aerospace Center. So let me jump in with the main idea straight away. In debiasing, we want to stop the network from extracting a specific feature. Therefore, we first divide the network arbitrarily into a feature extractor and a predictor. Image is fed into the feature extractor that calculates the representation. This representation is given to the predictor part of the network, and that makes a prediction. To ensure that this prediction is correct, we use a classification loss that compares the prediction to the correct label and then updates the weights in both parts of the network accordingly. In debiasing, we now use an extra loss, the debiasing loss, and this loss tries to enforce an independence between this representation, calculated by the feature extractor, and the bias variable. This loss is then used to also update the weights in the feature extractor. The main contribution of this paper is that we suggest to use a conditional dependence instead. So instead of the debiasing loss forcing the representation to be independent of the bias variable, we force it to be independent of the bias variable given the correct label. The rest of the paper is organized as follows. First, I want to explain when to use this new method, so what kind of bias are we going to tackle. Then I'm going to explain why we think that this new method is a better fit for this kind of bias. And here also we'll try to give a more formal explanation. And then I will present some experimental results. So when to use our method? We think our method should be used in situations where a meaningless feature co-occurs with a meaningful feature in the training set, but not in the test set. I want to give an example to explain it. Here, imagine that you want to build a system that predicts aquaplaning risks from a camera system in a car. For that, of course, we need a lot of images, some containing aquaplaning conditions and some containing safe conditions. Of course, it's easy to get a lot of images of safe conditions. You can just drive around on the street and take pictures. However, driving into aquaplaning conditions is very dangerous. Hence, all the images of high aquaplaning risk have to be taken in a specific facility where it is actually safe to drive into aquaplaning conditions. Hence, the road markings in the aquaplaning risk situation will look similar in the training set. However, this will not be the case during the actual use of the system in the wild. More formally, we have images and we want to predict the aquaplaning risk, and both the image and the aquaplaning risk is actually influenced by the amount of standing water on the street. However, the image is also influenced by other things like the road markings or the tarmac, and due to the creation of the training set, in this training set, the amount of standing water actually influences these road markings, and hence we end up with a biased training set. So this is the bias model for which we propose our new debiasing method. A signal, a bias variable, an image, and a label are connected as displayed in this graph. Of course, that does not fit every bias, but it fits many situations in computer vision, in addition to the one we already presented. There are many examples, for example, in medicine. However, there are also biases it doesn't fit, and many of those are in the category of algorithmic fairness, where the bias is often also present in the test set. But even given this bias model, why does this lead to conditional dependence being the better measure over unconditional dependence? And here we have two arguments. The goal of debiasing is to stop the network from using a specific feature. And to do this, however, we first need a way to measure whether a feature is actually used. And as explained in the main idea, previous work used the dependence between the feature and the prediction. And of course, if a feature is independent of the prediction, it cannot be used in its calculation. However, the inverse is not true. So if a feature is dependent to the prediction, doesn't mean that it is used. And this was actually shown by a paper in Understanding Deep Learning, and they proposed to use the conditional dependence condition on the label instead, and that is what we do. the second piece of motivation is a proof for a simple case. However, I don't think it's the best idea to go through the equations in this talk, so I'll just give you the more informal idea of why conditional dependence is or should be the better criterion in this situation than unconditional dependence. And for this, to our bias model, we also add the prediction, which is just a function of the image. And now what we want, the information we want the classifier to use, or the predictor to use, is actually this path where the signal, since it influences the label, should contain information on the label. This information can be found in the image, and the neural network should pick up this information from the image and base its prediction on this information. However, due to the bias variable, there's a second path for information, and this is that still the signal contains information on the label, and the signal influences the bias variable, and now this bias variable is also included in the image, and so the classifier can also use this part of the image to reach its prediction. And this is what we don't want. We don't want the classifier to use the part of the image which is information on the bias variable, and hence we want to discourage this path. And what previous work did was enforcing independence between the prediction and the bias variable. However, information from the bias variable can get into the prediction via two paths also. One is this direct path from the bias variable to the image to the prediction that we actually want to block. But the other one is, since the actual signal influences the bias variable, it will contain information on the bias variable. And this information is also included in the image, and it is actually the part of the image that contains the signal. And therefore, independence can only be reached if the classifier does use neither the part of the image which contains the bias nor the part of the image which contains the signal. And this is actually what we see in related work or in previous work, where the performance of the classifier drops due to debiasing, also on unbiased data. And this is because this link between the signal and the image is actually also targeted by the debiasing method. On the other hand, if we condition on the signal S, we block this path, and hence the only path we punish the classifier for using is this path, this direct path from the bias variable to the image, to the prediction, that we actually want to punish the classifier using. A formal proof for the case where all these arrows are linear functions and the label is a scalar variable is included in the paper. Before we can continue with empirical evaluations, we have to turn this conditional dependence criterion into a differentiable loss. And here we present three possible implementations of how to do this. The first is mutual information, or for conditional mutual information, where we have to approximate the probability density functions and then calculate the mutual informations. The second is a kernelized measure, the Hilbert-Schmidt dependence criterion, where we calculate kernel matrices and then can, by the similarity of these kernel matrices, can decide whether something is dependent or conditionally dependent. And the third is maximum correlation coefficient, where we use neural networks to approximate or to find the two functions which maximize the correlation between the two variables, or for the conditional case, the partial correlation. And before we come to now the empirical results, there's one more thing I want to talk about, and this is limitations of our method. And here there are mainly three. And the first is the bias has to be known. Of course, we cannot expect the method to be thrown at the dataset and just erase any kind of bias. As you saw, we need to calculate a conditional dependence between the prediction and the bias variable, and this is of course only possible if we can assign an exact value to the bias variable. Second, the bias model we presented earlier has to fit the data, and this is not always the case. We believe it's the case for many biases in computer vision, but certainly not all of them. And third, conditional dependence tests are actually harder than unconditional dependence tests. This is less a problem of time, but more a problem of numerical stability and finite data effects, finite sample effects. So finally, we can come to our empirical results. And here I want to present three experiments, or the results for three experiments. The first of which is on synthetic data. And here we built an image data set that contains two signals, the shape, which is a cross or a square, and the color. And in the training set, these two are linked. And in the test set, they are independent. And to avoid any deep neural networks prefer shape over color shenanigans, we run two setups, one where the shape actually determines the label and the color is the bias, and one where the color actually determines the label and the shape is the bias. And the results can be seen here. First, in orange you see the baseline model. The baseline model is just a neural network, no debiasing applied. And then you see four methods from the literature, none of which can outperform the baseline. The reason for this is, as we explained in the proof before, that debiasing also discourages the network from learning the correct signal. And then in blue, we have our three methods. And as you can see, our three methods actually outperform the baseline. Then we present an ablation study. In this ablation study, we build our methods again, but unconditional. And as you can see, all the conditional methods outperform the unconditional methods in both setups. So finally, we present one experiment on real-life images. And these are images of cats and dogs. And in the dataset, actually two signals are labeled. One is whether it's a cat or a dog, and one is whether it's light-furred or dark-furred. And to create biased training sets from this dataset, we start with a dataset in which all dogs are light-furred and all cats are dark-furred. And then we, for the next datasets, increase the fraction of dark-furred dogs and light-furred cats until all cats are light-furred and all dogs are dark-furred. And the results can be seen here. So three things: if all dogs are light-furred or all dogs are dark-furred, the fur signal can actually not be distinguished from the dog or cat signal. And if 50% of the dogs are light-furred, the two signals are actually independent. This leaves us with 8 proper bias scenarios. And out of this 8, our method outperformed the baselines and the literature methods in 7 out of this 8. Further, we compare the conditional and the unconditional use here of the Hilbert-Schmidt independence criterion as a loss, and we find that the stronger the loss, the stronger the bias, the stronger is the gain of using a conditional dependence method over an unconditional dependence method, which is expected. So thank you for your time, and I'm looking forward to questions.